Now we have transformations, and again, transformations haven't changed. They just look different because they're now in a logarithm. That a that's being multiplied by the parent function, the logarithm in the front, is still a vertical stretch. So it is a stretch if that absolute value of a is greater than 1. It's a compression if that absolute value of a is between 0 and 1. And again, we're focusing on the absolute value because if it's negative, if a is less than 0, then that means we're multiplying the y values by a negative, and when y values change from positive to negative, that means it's reflected about the x-axis. On the other hand, if it's our x value that's being multiplied by a negative, our argument on the inside, our x values are changing from positive to negative, that means it's reflected about the y-axis. Our horizontal shifts has to deal with that change in c. Notice where we have that minus c there with x. So it's going to move either left or right, but it's going to be in the opposite direction of the sign of our c. Our vertical shifts of that plus d at the end is going to move in the same direction as the sign of d. So notice none of those have changed from the exponentials or even the trig functions that we worked with. So let's look at example 3. We want to use transformations to graph this function, negative log base 2 of x minus 3 quantity and plus 1. You want to state the domain, the range, and the asymptote. Our parent function here would be y equals log base 2 of x. And we've actually graphed this function where we had x is 1, y is 0. If x is 2, y is 1. The next was 4, y was 2. 1/2 was negative 1, 1/4 negative 2. And so here's our original function, log base 2 of x. So now let's take a look at the transformations that are occurring. And remember, we have to do the reflections and the stretches first. Well, we notice at the beginning our a is negative 1, which just means it's reflected about the x-axis. In other words, we're changing all the signs of our y's. Well, we can do that first. Let's do that in green. So if we take the point 4, 2, we're going to shift it down to 4, negative 2. The point 2, 1 will go down to 2, negative 1. 1, 0 will stay at 1, 0. 1/2 negative 1 will move up to a positive 1, and the point at negative 2 will move up to a positive 2. So that is just the reflection. In other words, the negative log base 2 of x. We'll even write that underneath here. Here was step 1, negative log base 2 of x. Now we need to look at our shifts. So in step 2, since we have an x minus 3 and then a plus 1, that means we're going to shift right 3 and also shift up 1. So for everything, every point that we have, everything gets shifts to the right 3. That includes our vertical asymptote. Since our original vertical asymptote is at x equals 0, here, we're going to move it to the right 3 places. Here, x equals 3. And shifting it up or down 1 isn't going to make a difference because it's a vertical line. Now we take all of the points that's there in green, the one that's decreasing, it's been reflected, and we're going to take all those points, shift them right 3 and up 1. So starting with the point 4, negative 2, we're going to go right 3, 1, 2, 3, and up 1. Point 2, negative 1, we're going to go right 3, up 1. Point 1, 0, right 3, up 1. Then the point 1/2, 1, we're going to go right 3 and up 1. And the point 1, 4, 2 to the right 3 and up 1. So this last graph in black is our f of x functions with all transformations. Now they wanted us to state the domain, the range, and the asymptote of this new function. Now we can look at the picture to find the domain, but we can also look at just the argument. The plus 1 doesn't come into effect. Our argument was x minus 3. That has to be greater than 0. Add 3 to both sides. X has to be larger than 3, which is true. Our entire graph is to the right of that vertical asymptote of x equals 3. Our range does not change because it's going to continue to increase towards the left and decrease towards the right. So it goes from negative infinity to infinity, and we have a vertical asymptote at x equals 3. So in this example, they're giving us a function graphed that is a transformation of this parent function, y equals log base 3 of x, and we can rewrite that as 3 to the power of y equals x. They want us to find the equation for the function graphed below. So remember, we did this with exponentials, and sometimes it's a little give and take. We kind of see how the original function is transformed, and we take the graphed function and have to go backward. So let's first graph the parent function, log base 3 of x. If you need to, you can go ahead and do an xy table. But remember, there are 2 points that are pretty common regardless of what the base is. And that's an exponent of y will give you an argument of 1. So we have the point 1, 0. And if you had an exponent of 1, your argument and your base would be the same. So we get the point 3, 1. So there's our original parent function, y equals log base 3 of x. So we can guesstimate kind of what's going on here. First of all, we know that it is reflected across the x-axis. How do we know that? Well, this original function, the blue dotted, is increasing up to the right, but we want it to be decreasing left to right. So if we flipped it over the y-axis, it would be decreasing but going downwards. Okay, so we want to flip it over the x-axis. So that is reflected about the x-axis, which means we would be multiplying by some negative factor of a times log base 3 of x minus, I guess it was c plus d. So all we know now is the negative a part. So we can take those 2 points and we can reflect them over. So we get 1, 0 stays in the same place. 3, 1 comes down to 3, negative 1. So we'll just write that as y equals negative log base 3 of x. Now I'm going to go ahead and erase that original one so we don't get too confused, but you guys can do it in a different color. So this is the one that we're now focusing on. So these 2 points are 2 units away from each other. It's from 1 to 3. These 2 points are also 2 units away from each other. We are at negative 3 here and negative 1 there. So there's a couple of things that are occurring. One of the things that you may notice right away is our original y asymptote. Our original vertical asymptote was at x equals 0, and it is shifted left 4 units. Got to be careful. I saw that negative 5 there, and I did the whole problem wrong, shifting it left 5 units. But it's actually landing at negative 4. So that means if it's shifted left 4, then we would have a negative a, or I should say negative absolute value of a, log base 3 of x plus 4 plus d. But the problem is if I shift left 4, those shifts, either left, right, up, or down, are what's supposed to happen last. There might be a stretch in there somewhere, and we need to know what that stretch is. So what I would do is take the graph. We know it was shifted left 4 as our last step. Let's back up a step. Let's move that graph back to the right 4 units and compare. So if we move the point negative 3, 0 to the right 4 units, we would land here at 1, 0. And if we move the point negative 1, 3 to the right 4 units, we would land here at 3, negative 3. And our vertical asymptote would still be back where it was at 0. And now we can compare our y values. Well, the y value in our first point at 0 doesn't change. It's still 0. Remember, if you multiply 0 by any factor, it's going to stay 0. So that point's not going to move. But the point where x equals 3 is down here at y equals 1, and then it got moved down to y equals -3. This here got stretched by a factor of 3. So we need to write that in. We're going to stretch by a factor of 3. That means the absolute value of our a is 3. So our equation would be f of x equals the opposite of 3, or -3, log base 3 of x plus 4. And it doesn't look like anything was shifted up or down. We just had the left and right and the stretch. And you can always check these by putting it back into the table and seeing if you get the points that were given in the original graph. So if we plug in a -3 for x, we would get -3 log base 3 of -3 plus 4, which is -3 log base 3 of 1 equals y. And remember, the log of 1, regardless of the base, is always 0. So -3 times 0 gives us a y value of 0, which is one of the original points. The other original point is -1, -3. So let's plug in a -1 for x, which gives us a -3 log base 3 of 3 equals y. So log base 3 of 3 is a 1. So -3 times 1 is -3 for our y, which is the second point that was given. The equation that we came up with works. And again, you can also graph it in your graphing calculator and make sure that it matches the graph that is in our example. All right, folks, that is it for section 4.4. If you have any questions, please don't hesitate to contact me. You know where to find me. Thanks. See you soon.